a gas is heated in such a way that the temperature and the pressure of the gas increases. Whereas the volume is kept at constant. So generally when we heat a gas, as given in this example, that is a piston and a cylinder setup, so the gas will gain energy and it will tend to expand. So to prevent expansion, so this piston can be kept at a fixed position by using some kind of locking mechanism. And because of that, the expansion or the volume change can be prevented. So when the volume is not going to be changed as the gas gains energy, so this energy is going to increase the temperature and the pressure of the gas. And in this case, since there is no change in volume, so the work done due to a constant volume process will also be zero. So the heat energy that is added is solely used to increase the internal energy of the gas. So to understand this process better and to derive different thermodynamic properties, so let's visualize this process. So we can use a pressure volume diagram and let the initial state be 1, from which the pressure increases and the temperature increases without any change in volume to reach state 2. So there are two pressures, that is the initial pressure and the final pressure, and there is no change in volume. For the state 1, all the thermodynamical properties will be given by the subscript 1. And similarly, P2 represents pressure at state 2, then V2 represents volume at state 2, and T2 represents the temperature at state 2. And as we can see here, so the pressure increases, that is P2 is greater than P1. And since there is no area that can be drawn under the graph, since volume has only one straight line, there is no work done. So let's start with deriving the relationship between pressure, volume, and temperature. So this relationship comes from the characteristic gas equation. So the characteristic gas equation is PV equals nRT or PV equals RT. So we can write pressure volume by divided by temperature is a constant C. So when we apply the states, that is state 1 and state 2, so we can say P1 V1 by T1 is equal to pressure at the state 2, volume at the state 2, and temperature measured at state 2, that is T2. Since the process is a constant volume process, volume 1 and volume 2, that is volume at state 1 and volume at state 2 are the same. So this characteristic gas equation is going to become P1 by T1 is equal to P2 divided by T2, or we can rearrange this equation and write it as P1 divided by P2 is equal to T1 divided by T2. The work done in any moving boundary process is given as W is equal to the integral of pressure into the small change in volume. Or this can be rewritten as pressure into change in volume. So since there is no change in volume, that is since V1 is equal to V2, so the work done in a constant volume process is equal to 0. The change in internal energy can be given as the total change in internal energy is equal to mCv dt, that is the mass of the gas, the specific heat at constant volume, and the small change in temperature that causes the change in internal energy. Or we can rewrite this as or we can rewrite it as to find the heat transfer in this process, we can use the first law of thermodynamics. So heat transfer can be given as Q is equal to work done plus change in internal energy. Since the volume change in this process is zero, the work done is also zero, and therefore the heat transfer is equal to the change in internal energy, which is equal to the change in enthalpy in constant volume process can also be derived from the formula of enthalpy, that is enthalpy is equal to internal energy plus pressure volume product. And since PV is 0 here, change in enthalpy is going to have the same expression as change in internal energy, which is equal to mCv dt, or we can also write it as or we can also write it as to summarize, during constant volume process, the work done is 0, so there is no work done, and there is change in internal energy, which is equal to and there is heat transfer, which is again equal to the internal energy or the change in internal energy due to the process, and the enthalpy is again going to have the same expression as the change in internal energy, that is mCv T2 minus T1.